This is Math 251, and we're at the very beginning here going to start by taking a look at three-dimensional geometry. One of the things that you'll find out about Calc 3 is that a lot of what we're going to do is going to be extending on patterns that we started to build back in Calc 1 when we didn't have three dimensions. And so as you'll see on this first page, I'm going to begin by just kind of showing you some patterns that we can start building already. This is a common theme that's going to run through the course. So when I start talking about locating a point, I'm actually going to start by taking you all the way back to about first grade. The first points that you ever learned to locate were just one-dimensional points, single values on a number line. So if I have a number line here, I could, of course, locate some single point x anywhere on that number line. This is a one-dimensional point. And we can just say it's in the set of real numbers. The other thing I would like to point out here is that the origin, 0, kind of splits our space, our one-dimensional space, into two parts, right? This part, which is a set of negative integers, or actually not negative integers, negative real numbers, and this side, which is the set of positive real numbers. So this space neatly splits into two parts. All right, let's next kick ourselves up a few years into maybe middle school or so when we first started looking at plotting two-dimensional points. We now have a Cartesian or rectangular coordinate system. And we get that by taking not just one number line, but two number lines, right? Specifically, two perpendicular number lines. Points are now two-dimensional. They have both an x and a y value, up here or something like that. They are located in what we would call two space, which we write like that. R squared is what it looks like, but it's read as two space. And my two axes here that meet at the origin split my two space into 1, 2, 3, 4 sections, which we typically call quadrants, right? 1, 2, 3, and 4. All right, I've only got two things so far, which doesn't really establish a pattern, but let's see if we can continue this now into three space. If I want to plot a three-dimensional point, instead of having two perpendicular number lines, I'm going to need to locate my point using three perpendicular number lines. Now, it's impossible to truly draw three perpendicular number lines on a flat piece of paper. So when we draw, we usually try to give it some perspective, which is what you're seeing here. The y-z plane, right? There's the y-axis and the z-axis. I'm going to draw flat in the plane of the paper. And then the x-axis looks like it's at an angle, but all that really means is that it's coming out of the plane of the paper. We're just showing the perspective. In actual reality, that x-axis would be perpendicular, coming straight up from the origin. But we can't draw it like that. So notice we do have three perpendicular number lines, right? 1, 2, 3, all at right angles to one another. To locate a point in three space, then, I'm going to have to give all three coordinates, an x, a y, and a z. That's a point in three space, R3. And I'll also have you notice that each pair of axes forms its own coordinate plane. So just the y and z axis makes a plane that's flat in the plane of the paper. Not surprisingly, we would call that the YZ plane. If you come over to this next picture, the green plane here contains the Y and the Z axes. So the green plane would be the YZ plane. Similarly, this yellow plane that contains the X and Z axes, we would call that one the XZ plane. And finally, the one that's actually horizontal here contains the X and Y axes. So there's my XY plane. Now I should warn you, it's actually arbitrary which axes we draw where. They could have been in any order. Typically, this is the way that you'll see them in at least this math book and in most math books. Physics books sometimes draw them in a different order. They can be drawn in any order, so when you do look at a problem, be careful, make sure you note which axes are where. One thing I will tell you in this class, we will always use what's called a right-hand coordinate system. And what that means is that if I were to take my right hand, I'm going to put my wrist at the origin, and I'm going to line my fingers up along the x-axis and curl them toward the y-axis. Let's see what would happen. So the x-axis is technically pointing straight out, so my hand would be straight up, and I'm going to curl my fingers toward the y-axis, and notice that my thumb ends up pointing up. Up is the positive z direction. Because that's true with my right hand, this means that I am in a right-hand coordinate system. Left-hand coordinate systems do exist. If this were a left-hand coordinate system, I would have done that same thing with my left hand, and my thumb would have ended up pointing down. And so the positive z-axis would have been pointing down in a left-hand coordinate system. As I said, in here we will be limiting ourselves to right-hand coordinate systems, but I just wanted to mention they do exist. All right, if you look at this picture with the planes kind of shaded in, can you see how many pieces the space has been split into? We have 8, right? There are kind of 4 upstairs apartments here and 4 downstairs apartments. So this setup splits our space into 8, which we typically call octants. Now I want to talk just a little bit more about this idea of extending patterns. Could we do 4-dimensional point plotting? Well, first of all, ask yourself what would be required. It took 2 perpendicular lines, or 2 perpendicular number lines, to create 2 space. It took 3 perpendicular number lines to create 3 space. To create 4 space, I would have to have 4 perpendicular number lines. That's not something we can draw or even visualize because we live in a 3-dimensional world. However, mathematically, we can still mathematically say, hey, yeah, that's possible. 4 space would just be 4 perpendicular lines. And in fact, if that were possible, how many pieces do you think the space would be split up into? Well, if you look at the pattern, 2 parts, 4 parts, and now 8 parts, they're all powers of 2, right? So if I were to be able to divide a 4 space, it would make sense that it would be split into 16 parts, and so on. So when you see mathematicians talk about 4 space or even 5 space or 6 space or higher, we're no longer talking about something that's physically visualizable, but mathematically it makes sense based on the patterns. All right, let's talk just a little bit more about the structure of 3 space. On our next page here is a picture that just shows the various octants. Notice our planes are labeled up here, just like we did ourselves on the previous page. And I'd like to point out that octant 1, which is the only one I'll actually ever refer to by name, is the octant that contains the positive x, positive y, and positive z axes. So octet 1, all three variables, x, y, and z, are all positive. The other octants go around counterclockwise. So this would be 2, 3, and 4. And then below, we've got 5, 6, 7, and 8. They're there. You can take a look at them. But other than octet 1, I really won't refer to them by number. All right. So the next question I want us to ask ourselves is, how do we plot points in 3 space? Unfortunately, the answer is with a great deal of time and effort. We won't do a lot of this, but I want you to see at least one. Here's what's going on. If I've got this point P with coordinates A, B, and C, probably not surprisingly, what that means is come out A units in the x direction, go over B units in the y direction, and then go up C units in the z direction. And as long as I include these little guidelines, right, these little arrows, it's possible to see what I mean, where that point is supposed to be located. But look at what happens in the second picture when we don't include the arrows, the little guidelines. It's really impossible to tell where that point is located. Perhaps this point is really just flat in the YZ plane. Maybe x is 0, right? We can't tell because we don't have the perspective of the guidelines. So when we really, really need to plot a point in 3 dimensions by hand, and we won't do this much, we have to go ahead and have some technique that allows us to see those guidelines to determine the perspective. I like to do this using what I call a box method. If I'd like to plot the point P, and this one's just generically x, y, and z, I make a little box. Notice we've come out x units along the x-axis, y units on the y-axis, and then z units up.